Hello, we are Nagyong-ha, Yewon Kim, Hanyeong Lee from Team Kim Hanyeong. Our topic is as shows. First, let me explain the problem. Our AI is a way to maximize rehabilitation outcome after ACL reconstruction, or athletes after ACL reconstruction, in order to improve return to sports outcomes for sports teams and sports medicine centers. The healthcare need is that the overall quality of evidence for current guidelines is low, and clinical practice still relies largely on clinician experience and institution-specific practices. ACL injuries are extremely common in athletes, and poor recovery can become career-altering. Yet there is no unified rehabilitation protocol. Even when the same rehab protocol is applied, outcomes vary widely because recovery depends on many contributing factors. So it is necessary to provide rehabilitation with an individualized protocol. This indicates a potential need for patient-specific prediction models. The population, outcome, and payers are as follows. Second, the solution. We build an AI-based clinical decision support model that predicts rehabilitation outcomes after ACL reconstruction by integrating surgery injury-related factor, patient-related factors, and rehab process factors. The model is trained on real-world ACLR data and learns to predict key outcomes, quadriceps index, hop test, etc. For a new patient, clinicians enter patient features and the rehab plan they are considering. The AI then predicts expected outcomes for that protocol and allows side-by-side comparison across different rehab strategies. This supports truly individualized rehabilitation planning, aiming to improve return to sports success. And this is the AI approach and methodology we have planned.
The system explains which factors are most influential for each individual patient's recovery. We put specific patient data for demonstration. He is 26-year-old professional soccer player at 7 months following ACL reconstruction, receiving high-quality post-operative rehabilitation. On the left side, structured patient inputs are entered into the system. The details of the input variables are shown here. In the Individual Explanation tab, the model displays predicted values across 5 key outcomes: quadriceps index, IKDC score, knee extension ROM, Ligament grade, and hop test battery. And these outcomes can quantify the effect of the rehab protocol. And using these 5 domains, the model can further estimate RTS probability. This is not a validated index, but can provide a pragmatic and clinically relevant index for the functional recovery. In this case, RTS is 100%, and this patient is ready to return to sports. So we now move to the weights tab, which represents the core component of this AI demo. It is about SHAP, which quantifies the individual contribution of each input features. So the patient-level SHAP identifies subject-specific contributors. In this patient, adherence is the dominant contributor to the quadriceps recovery, which means that improving adherence may have the greatest impact on recovery. It counts like 24.6%. And if depression receives high value, then psychological support may be an important intervention point. So to wrap up, patient-level SHAP enables patient-specific stratification, which traditional rehab guidelines couldn't do. And now move on to the population-level SHAP. On the other hand, this analysis covers the entire cohort. It is not patient-specific but protocol-oriented. In this dataset, adherence and total rehab duration have high value, suggesting regulatory targets for the universal rehab protocol design. In the summary, this system not only predicts rehab outcomes but also provides patient-specific suggestions for better rehab outcomes. So also, it can help design evidence-based rehab guidelines for common good. Rather than replacing clinicians, this AI system is designed to support clinical decision-making with evidence.
The model integrates naturally into the rehabilitation workflow. After surgery, athletes return to the clinic where clinicians and physical therapists enter patient factors as well as injury and surgical details. The model then helps clinicians select the most appropriate rehabilitation plan, including sessions frequency, supervised to home ratio, and so on. And during follow-up visits, updated information such as patient adherence is added, allowing the model to refine the rehab strategy over time. Also, researchers can use job values to identify features that may be helpful to explore further. And the deployment happens in 4 steps. We train the model on a secure dashboard, integrated through a cloud API, and validated across multiple centers. And if needed, we then connect it to EHR or athlete monitoring systems. We also address limitations such as small datasets and potential bias, and maintain safety by ensuring that AI only supports and never replaces clinical judgment, while all data remain fully de-identified and IRB compliant to ensure health data privacy. Our next steps focus on expanding data, refining the model, and preparing for real-world deployment. First, we'll partner with a bidder to collect 30 to 50 de-identified cases and build version 1 of our model, and create a standardized data schema and test our clinician-facing dashboard with several sports medicine clinicians. Next, we plan to expand to a multi-center dataset of over 100 patients, which will allow us to add time series modeling and protocol optimization. And with more resources, we aim to generate deeper job-based scientific insights, like test-optimized protocol variations, and also incorporate richer features like biomechanics, psychological readiness, and wearable sensor data, and so on. Ultimately, we believe these steps will allow us to maximize the return to sport outcomes for athletes recovering from ACL reconstruction. These are the references, and thank you for listening.